Now today's topic of discussion is heating effect of electric current. Okay. Now we know that the battery or a cell is source of electrical energy. Try to understand, battery or the cell is providing the energy in the circuit. Okay, it is not producing electron. The chemical reaction within the cell generates the potential difference between its two terminals that sets the electrons in motion to flow the electric current. Okay, we have also seen that to maintain the current, the source has to keep expending its energy. Now, where does this energy go? Some part of the source energy in maintaining the current may be consumed into useful work. So, some energy is going in moving, or rather to keep the electrons in motion. Rest of the source energy may be expended in heat to raise the temperature of the gadget. Now you have seen that for a long time, if you are keeping the fan on, then if you touch the dial of the fan, then it becomes hot. So some energy is used, or rather it is expended, or it is wasted in the form of heat. Okay. We often observe this in our everyday life. For example, an electric fan becomes warm if used continuously for a longer time. On the other hand, if the electric circuit is purely resistive, that is, a configuration of resistors only connected to the battery. Whenever any resistor is connected to battery, say for example, if you have a one resistance which is joined with the battery, then what will happen? The resistance will become hot if you keep the current on for some time. So that circuit is a resistive circuit, so energy is utilized or it is dissipated in the form of heat. This is known as the heating effect of electric current. This effect is utilized in devices such as electric heater, electric iron, etc. So there are certain devices in which the heating effect of electric current is necessary, like this electric heater, electric iron, toaster, etc. But when you talk about electric fan, then the heat which is generated is considered to be the electrical energy wasted in the form of heat. Okay. Now we consider the electric current I flowing through the resistor of resistance R. Let the potential difference is V. Okay. Let T is the time during which the charge Q flows across. So you have a circuit in which there is say for example, there is a resistance which is joined, say for example, okay, one resistor is joined, okay, and a battery is kept here whose potential difference is V, and say I amount of current is flowing for some time, that is T. Okay, now as you know that the work done in moving the charge Q through potential difference V is VQ. So W, that is work done, is equal to W is equal to V into Q if you want to move the charge Q. Therefore, the source must supply energy equal to VQ in time T. Hence, the power input to the circuit by the source is, power is nothing but work upon time. As you know, power is equal to work upon time. So if you write, instead of this W, we write V into Q, then the formula for the power will become P is equal to VQ upon T. And as you know, Q upon T is electric current, so we can write P is equal to VI, that is V into I. Okay, so this is very easy to understand. Okay, so as you know, first of all, power we know it is W upon T, and W is the work done. W is the work done. W is equal to VQ. So instead of this W, if you write VQ, then power will become VQ upon T. And as you know, Q upon T is current I. So power will be equal to V into I. Okay. So as you know, again, power is nothing but work upon time. Still you can go further. Power, what is power? Power is work upon time. So work upon time is equal to as such Vi. So we can say work done, that is energy utilized, is V into I into T. And this energy which is utilized, or which we can say that this energy is producing heat. Okay, so we can say that a steady current I, if it is flowing, then the amount of heat which is produced in time t is given by this W is equal to VIT. Okay. So this part is explained, or you can consider this circuit as an understanding, okay, which I tried to explain. Here the potential difference is V, amount of current which is measured by the ammeter is I, resistance is R, okay, and the value of with heat which is produced, that is W, is equal to, as you know, it is VIT. Now as you know, according to Ohm's law, V is equal to I into R. So instead of this V, if I write IR, then this becomes I square R into T. So amount of heat which is produced if the current is passed through the resistance R for time T, if that current is I, then amount of heat which is produced can be given by W is equal to I square RT. This is known as Joule's law of heating. Okay, this equation which we got, I square RT, is the Joule's law of heating. Okay, so you can just go through this. Okay. This is known as Joule's law of heating. The law implies that heat produced in the resistor is, you can see, heat produced in the resistor is directly proportional to the square of the electric current for a given resistance. It is directly proportional to the resistance of a given current. If more resistance is there, then for a given current more heat will be produced. And it is directly proportional to the time duration for which the current flows through the resistor. If you have more time duration, then more heat will be produced. Say for example, if you have a fan which is on for half an hour, and if the other fan is on, same quality fan, same brand fan, same rating is there, okay, then if you keep it for say 2 hours, then more heat will be produced, or we can say its dial will become hotter than the fan which is on for half an hour. Okay. So more the time, more the heat will be produced. This is obvious from this equation. More the current for a given resistance, then more heat will be produced, because heat is directly proportional to the square of the electric current passing through the given resistance. Okay. So this equation is the Joule's law of heating. Okay. In practical situations, when an electric appliance is connected to a known voltage source, which is, okay, in equation 12.21, which is here, is used after calculating the current through it using the relation I is equal to V upon R. Okay. So this is very easy to understand. Calculations can be done here. An electric iron consumes energy at a rate of 840 watt. So power is given when heating is at a maximum rate, and 360 watt when the heating at a minimum rate. Voltage is 220. What is the current? It's very easy to find. As you know, P is equal to V into I. So P is equal to V into I. So now I is made subject of formula I is equal to power upon voltage. So current can be found easily 3.82 ampere, and the resistance of the electric iron R is equal to V upon I. So V is 220 volt, current which we got 3.82, so 57.6 ohm will be the resistance. So when the heating is at maximum rate, the current is 3.82 ampere, okay, and the resistance is 57.6 ohm. When the heating is at minimum rate, okay, the power is 360 watt, okay, so 360 upon we make V, okay, 360 instead of power we write 360, voltage is same 220, so current is 1.64 ampere, and at that time the resistance of the electric iron is 134.15, okay. Another example, again very easy, 100 joule of heat are produced each second in a 4 ohm resistance. Find the potential difference across the resistor, okay. Now from this equation which we have derived, okay, as you know, heat produced H is equal to I square RT. H is equal to I square R into T. Now if you want to find I square, then it becomes H upon R into T. So I will be equal to under root of H upon R into T. All the values are given, heat is there 100 joules, so instead of H we write 100, okay. Then resistance is 4 ohm, okay, and time is per second, so 1 second, so you get I is equal to 5 ampere, very easy to calculate, and V is equal to IR. So 5 ampere into 4 ohm resistance, so this becomes 20 volt as our voltage, okay. Now there are certain questions, okay. Why does the cord of electric heater not glow while the heating element does, okay? Because what will happen, heat is utilized there, okay, and totally it is converted rather in the form of heat, okay, so it does not glow, okay. Compute the heat generated while transferring 9600 coulomb of charge in 1 hour through a potential difference of 50 volt, okay. So compute the heat generated. You can use this formula which we have discussed here, okay. P 1 hour it is, okay. So heat generated is VIT, okay. You can easily calculate this. As such, heat generated is nothing but W, that is work done, and as you know, W is equal to V into Q. Now see, here voltage is given 50 volt and charge is given 96000. So just we have to multiply these two quantities and you will get the heat generated, okay. The time 1 hour, as such it is not needed here, it is just given, okay. An electric iron of resistance 20 ohm takes a current of 5 ampere. Calculate the heat developed in 30 seconds, okay. You can calculate this by using the equation heat developed is equal to this question I am talking, H is equal to I square R into T. Now see here, I square means square of 5 ampere will be there, resistance is 20 ohm, time you take as 30 seconds and calculate, you will get easily the value of the heat which is developed in 30 seconds, okay. Now there are practical applications of heating effect of electric current. The generation of heat in conductor is an inevitable phenomenon. Try to understand, whenever the current passes, heat is going to be generated in more or less amount. In many cases, it is undesirable. Try to understand, when fan is on, heat is produced, that is undesirable. We want to convert the electrical energy into mechanical work, but some amount of heat is definitely going to be generated. In electric circuit, the unavoidable heating can increase the temperature of the components and alter their properties. So this heating effect is as such, it is not needed, and it is giving different characteristic of a particular circuit. However, heating effect of electric current has many useful applications. The electric laundry iron, electric toaster, electric oven, they are using the Joule's effect, that is heating effect of electric current. The electric heating is also used to produce light as in an electric bulb. Okay, here the filament must retain as much of the heat generated as it possible so that it gets very hot and emits the light. So heating effect of electric current is used in the filamental bulb also. It must not melt at such high temperature, and that is why the tungsten is used whose melting point is very high, and this melting point is about 3380 degrees Celsius. Okay, the filament should be thermally isolated as much as possible using insulating support. Okay, the bulb are usually filled with the chemically inactive nitrogen and argon gases to prolong life of filament. So which gases are filled? Nitrogen and argon gases are used in the bulb. Most of the power consumed by the filament appears as heat, but small part of this power which is consumed is radiated in the form of light. Okay. Another common application of Joule heating is the fuse used in the electric circuit. Fuse, as you know, whenever more amount of current is passed through the wire, that fuse wire gets melted and our house appliances or home appliances can be saved. Say for example, in your house, we need say 5 ampere current, and if the voltage increases and if it becomes say 5.5 or 6 ampere or 6.5 ampere current, and if that current passes through the different appliances which are working as such on 5 ampere, so those appliances may damage. So this fuse wire, what happens? It has a particular rating. It has a capacity of say 5 ampere which can be passed. Now if more current passes through that fuse wire, then that fuse wire melts. Okay, it melts and the circuit is broken. So the appliances which are used or which are joined in the circuit, say fridge is there, say one TV is there, then the current will stop flowing through this. Higher amount of current will not flow, and these appliances can be saved because of breaking of the fuse. Okay, or fuse wire gets melted. Okay, now electric power we talk about. Okay, power, as you know, it is V into I. Very easy to understand this part. Power is voltage into current. Okay, now as you know, V is equal to I into R. So instead of V, if we write I into R, then this becomes I square R. And if you substitute instead of I, we can write V upon R. We can write V upon R. So if that power can be written as, keep V as it is, and instead of I we write V upon R. So V upon R into V will become V square upon R. So power has two equations here in terms of I and R and V and R. That is I square R and V square upon R. Okay. The SI unit of power is watt or joule per second also sometimes we take. It is the power consumed by a device that carries 1 ampere of current when operated at potential difference of 1 volt. Okay, if you have say 1 ampere current through a device and has a potential difference of 1 volt between the two ends of this device, then we can say that 1 watt power is consumed or 1 joule per second energy is utilized, or we can say it is 1 volt ampere. Now this watt unit is very small, therefore in actual practice we used unit of power, unit of energy as kilowatt hour. Okay. Now kilowatt is nothing but 1000 watt. Kilowatt is the unit of power as such. kilowatt hour is the unit of energy. Okay, since electrical energy is the product of power and time, see, try to understand, power is work upon time. So energy, that is work is nothing but W is equal to power multiplied by time. So electric power multiplied by time will give you the electrical energy. Now if you just take the product of power, that is 1000 watt, power is 1000 watt, and time duration for which the current passes through a device is 1 hour. Okay, so 1 kilowatt hour energy is obtained, and that 1 kilowatt hour energy is nothing but 1 kilowatt, that is 1000 watt. Hour means 1 hour time is 3600 second. So if you multiply, then 3.6 into 10 raised to 6 watt second energy or joule energy is produced, or we can say 3.6 into 10 raised to 6 joule energy. Okay, so this is a very easy topic. An electric bulb is connected to 220 volt generator. The current is 0.5 ampere. What is the power of the bulb? The power is V into I, as you know. So just we have to multiply the voltage and current, we get the power. Okay. Then electric refrigerator rated 400 watt operated 8 hours a day. 8 hours we are using. What is the cost of energy to operate 30 days at the rate of 3 rupees per kilowatt hour? So again we just find out the total energy utilized. Okay, in one day it will be 400 watt into time. See, power multiplied by time is nothing but energy. So energy utilized in a day is nothing but 400 watt multiplied by 8 hour. And if for 30 days we want to calculate, then multiply by 30, that is number of days. So total 9600 watt hour energy is utilized. Okay, so if you divide it by 1000, then you will get 96 kilowatt hour or 96 unit energy is utilized, and 1 unit is having the cost of 3 rupees. So total 288 rupees bill will be there, that for the utilization of the refrigerator. Okay, thank you very much. Here there are certain questions which are very easy. Okay, what determines the rate at which energy is delivered by a current? Okay, try to find the answer. Okay, an electric motor takes 5 ampere from 220 volt line. Determine the power of the motor and the energy consumed in 2 hour. Power is V into I, easily can be calculated. Okay, energy consumed is nothing but VIT, you can write formula. Okay, energy consumed W is equal to VIT. Voltage is there, current is there, time 2 hour means 3600 multiplied by 2, that is 7200 seconds you have to write, and you will get the answer. Okay, thank you very much. Here this chapter is getting over. Okay, try to solve the questions which are discussed. Okay, thank you very much.